In order to prove this, we need to apply Cauchy's mean value theorem. If you remember, you have two functions, f, capital F, and g, such that they're continuous and differentiable in this interval a b. Then we have this thing, right? F minus f at b minus f at a, g at b minus g at a is equal to the derivative of f at some point c in this interval divided by g prime at c. Right? This is Cauchy's mean values here. Okay. Now the idea of the proof is to define some functions capital F and capital G, so that this part of Cauchy's theorem, this fraction, is equal to the difference, right, between f and the polynomial divided by x minus a to the n plus 1. Okay, because that way we can get an expression for this coefficient. Okay, so the idea is how we can we define f and g so that this fraction is f minus p divided by x minus a to the n plus 1, and then in the right hand side we're going to have this expression, right? So let's start with the definition of this capital F, and we say this is f at b minus, and then we have the polynomial nx at b, right? So then we have this is going to be it, and then we have g at x is going to be b minus x to the n plus 1. Okay, now so let's just note that p and x at b is the sum from k equals 0 to n of the kth derivative of f at x times divided by n factorial times b minus x to the k, right? So now this is not a polynomial anymore, right? You see, this is a function of the derivatives of f times a polynomial, so it's a complex combination of things. But we'll see that if we evaluate this, we take p at some function at some point whatever, it's going to be a polynomial. Okay. Also, f and g are differentiable in this interval, right, around a, right, because this is just a function of the derivatives of f, and this is a polynomial, so this is going to be differentiable everywhere, right? Now let's compute the values of f at b and a. F at b is going to be f at b minus p and b at b. Okay, so this is the Taylor's polynomial of f evaluated at b, but the approximation is at b, so we know that the approximation is perfect at b, so this is going to be 0. Now f at a is going to be f at b minus p and a at b, which is this subtraction that we want to evaluate. This is going to be the remainder at b, if you want, so we can call it like that, but let's leave it like that. And then we have g at b is going to be 0 again, and g at a is going to be a minus x to the n plus 1, right? Is this correct? Yes. Sorry, a minus b minus a. Yes, b minus a to the n plus 1, right? Now we have this 0 minus f at a divided by 0 minus g at a is equal to f at a divided by g at a, which is f at b minus p and a at b. Again, this is the remainder of our polynomial at b, which is what we want to evaluate, divided by b minus a to the n plus 1. And this is going to be equal to the derivative of f at g at c and the derivative of g at c. Okay, now let's compute the two derivatives. Okay, let me go back to so g prime, this is the easy one. G prime is obviously n plus 1 times b minus x times minus 1, right? Because there's a derivative here, sorry, a minus sign here. And now we have to evaluate the derivative of f, right? But this is constant, and we just need to evaluate the derivative of this. So we have f prime at x is minus pnx prime, okay? And this is going to this expression, this is minus, and then we have this here, when k equals 0, this is f at 0, f at x, sorry, plus, and then the sum from k equals 1 to n of f, the k's derivative, times k factorial b minus x to the k, right? Now, this is the first, let's see, the first term is f prime, right? And then we have the sum from k equals 1 to the n, and then the derivative of this. Now, the derivative of this is the derivative of the first term, which is f to the k plus 1 at x. It's not f to the k plus 1, sorry, it's the k plus 1's derivative of f divided by k factorial times b minus x to the k, and then we have plus the derivative of this. So we have the kth derivative of x, of f at x, then we have k, but divided by k factorial we have k minus 1 factorial, right? And then we have b minus x to the k minus 1 times minus 1, because that's what the coefficient of x is, right? Now, and then we have this. Okay, this is all equal to minus this. So now this is going to be minus, and then we have, well, let's say, let's write it like this. Minus f prime at x, and then we have minus, and then you see that this sum is going to be telescoping, right? Because this is k plus 1, k, k minus 1, k minus 1, right? So this is something at k plus 1 minus something at k. So let's see, the first term is going to be f, the second derivative, at, divided by 1 factorial times b to the x, so b minus x to the 1, and then we subtract the first derivative of x divided by 0 times, and then when k equals 1, this is 0, so this is f prime at x, sorry, minus this, right? This is minus all of this sum, and the first term is negative, and then every term gets cancelled out, right? So the next term here is the second derivative divided by 1 factorial times b minus x to the 1, which is the first term in the previous sum, and so the second term here is the third term, the fourth term, and so on, right? So the last term remains is here, which is plus f to the nth plus 1 derivative of f at x divided by n factorial times b minus x to the n. Okay, this is going to be the last term in the sum. Okay, if you compute the telescoping series, you'll see. But then we have minus f prime minus f prime, which is 0, and then you have this is equal to minus the n plus 1 derivative of x at, or f at n divided by n factorial times b minus x to the n, right? And then if we want to approximate, go back here, right? So we had that f at b minus f at a divided by g at b minus g at a. This was equal to f at b minus pn at a, sorry, pn a at b divided by b minus a to the n plus 1, and then the derivative of f at c is going to be minus f n plus 1 at c divided by n factorial times b minus x to the n, and all of this divided by the derivative of g prime, which is wait a minute, this is going to be, yes, so minus, right, minus 1, let's say, n plus 1 times b minus x, right? And well, but this is, sorry, this is evaluated at c. So this is f, the nth plus 1 derivative at c times b minus c to the n, yes. And then, sorry, this derivative was minus n plus 1 to the n, right? And so we have minus n plus 1 times b minus c to the n. Okay, this is g prime at c, right? And now we have, you know, the minus and minus go away, b minus c prime to the n, b minus c to the n go away. And then we have that the difference between f at b and the polynomial at b, which is the remainder, remember at b, is equal, if you multiply by b minus a, to the n plus 1 derivative at c divided by n factorial, sorry, n plus 1 factorial, right? This is n plus 1 factorial times b minus a to the n plus 1, which completes the proof. Okay, this is the form that we were looking for.